Okay, hi everyone. We're going to get started. This is going to be the last theory seminar of the semester. I'm very excited today to introduce Rico. Rico is a good friend and was my postdoc host. Um, he is currently oh, he's currently a professor in the Department of Mathematics at ETH Zurich. He previously held a position. We'll see how good I can go in your history. He previously held a position in the Department of Applied Math and Statistics at John Hopkins.
Yes.
John, yeah. The S goes somewhere.
It's Johns Hopkins. Yeah.
Two S. And he has a PhD also from ETH Zurich, and he did postdocs at both a short one at EPFL and a longer one with Michel Gomans at MIT, where he is right now on sabbatical. I guess, yeah, Rico holds the unusual distinction of being somebody that's done a lot of foundational work in theory, and in particular in combinatorial optimization and network design and approximation algorithms, but he also has like his foot strongly in the industry door and does a lot of more sort of like practical projects applying techniques from optimization and combinatorial optimization. I guess he's like the reason that Swiss trains run quickly, I'm told.
That's too much, Alice, but thank you.
That was probably true before he was there.
And yeah, with that, I'll let Rico get started.
Yeah, thanks, Alice. Thanks a lot. And yeah, thanks for being here. It's a pleasure to be here. So let me talk about I would like to talk about the matrix secretary problem. That's and the specific model thereof. But actually, this talk has two goals. I mean, one is to talk about that specific model, but more importantly, I want to introduce you to the secretary problems and specifically to the matrix secretary problem, to some challenges that we have there, and to give you a better global understanding of it. And the next shows that the specific model will be a link to that. So it's less about just that model. And that's joint work with Richard Santiago and Ivan Sergeyev. And let me just start. And if you have questions, just interrupt me. I think it's easiest. So what is the secretary problem? It's a problem that got quite popular in the 20th century, in the middle of the 20th, in the 60s or 70s roughly. And its basic forms as follows. You want to hire, and let me just stay in the terminology of the times, you want to hire a secretary, and you interview a certain number of candidates, let's say n candidates here, and they will be interviewed in uniformly random order. And the way it works is you want to hire a single one. When you interview one of them, you will see how strong that candidate is, and this will be revealed by what I call a weight. The higher the weight, the better. Now the game is the following. You have to decide immediately and irrevocably whether to hire that one or not. Of course, having seen the first candidates, maybe not a good idea to hire that one. We have absolutely no idea what the weights are, so we keep watching a little bit. Let's say number 5. I mean, the one with weight 5, probably also we don't want to hire that one too. We keep going. Maybe at some point, here we have a candidate with weight 11. We maybe say, okay, let's hire that one. Of course, we would have preferred to hire the one with weight 14, but that one passed. And as I said, decisions are irrevocable. So if we did not hire at that point, we cannot hire in hindsight. So far, so good. Does the model make sense? So important is that, so the weights, they're just hidden, but they're there, right? And so an adversary can, if you do a worst case analysis, can choose those weights, but has to choose them up front. And then candidates are interviewed in random order. Random order is very important because it allows you to learn, right? By observing a constant fraction, you get an idea of the weights. If the order were like adversarial, it would be essentially impossible to learn. An adversary could show you first weights that don't make any sense, and you would know nothing about what's happening later on. Okay, good. Or maybe, well, let me start with first observation. It's not so hard to find a strategy to hire the best secretary with constant probability. Let me give you a very easy strategy that does that. Let's do the following, and this reveals a general theme in how people design algorithms in that context. Let's first do the following. Let's observe 50% of the candidates without doing anything. You don't even try to hire. It's just trying to learn. And then in the second phase, in the second 50%, let's try to hire the first one that is better than the best one you've seen so far. Okay. So you can imagine what happens is if you have the second best candidate, maybe I should just write things. Say the second best one is here, and the first one, the best candidate, happens to be in the second half. Whenever this happens, you're going to hire the best one, right? I wrote it also again here. So this happens at least with probability of order. And it turns out that you can actually, This is actually the best strategy, but not by observing 50% first, but by observing a 1/e fraction. And this is called Dinkin's algorithm and will lead to, so 1/e fraction, and this will lead to hiring the best candidate probability 1/e. So maybe it's not so surprising. That's really a stopping time problem, right? I reveal random variables to you, and you have to stop at some point. That's why people at the beginning who studied that were mostly probabilists working on stopping times. Now, but then one could say that that field was somewhat a bit more quiet for a few decades, but later on people got more excited about it again, but in variations of the problem where you can hire more than one secretary. And the reason is that this has a lot of interesting links to mechanism design. Let me give you just one model that will be actually a special case of what I later introduce as the matrix secretary problem. So here you see a network. We have a single, let's call it a server or a source, a single server, and we have different clients. The network has edge capacities. And let's assume that let me just make up a story to explain the setting here. Let's assume that we're selling a service to our clients. And the service we sell is a unit connection to the server. So this will just be a single path. So let me maybe do an example here. So I can serve that one here. For example, let me do something maybe slightly weird. Let's do it this way. I could serve that client that way with a unit path. This is an edge I can use 3 times with my path. But here the capacity is reached. I cannot use this edge anymore. So now I would have served that client. I could also serve this one as well, even both of them. If I want to do so, now I have to reroute the blue one. But that will be okay. So I don't really care how we serve them. I just have to make sure whenever I accept 2 clients and tell them, oh, I can serve you, that there exists 2 paths, to unit paths from the source or the server to the clients, not exceeding the capacities. So don't think too much about the routing. Important is that the routing exists. And so now you can imagine that I will interview, or actually I will talk to the clients in some random order and learn how much they're willing to pay, and I have to either accept or decline whether I want to serve them. So it's like the secretary problem from before, right? Just the only difference is that I can pick more than one under some constraints. The network gives the constraints. Right? Does that make sense? Yeah? Perfect. And of course, you can model the problem from before this way, right? You could just have a server, a single edge of unit capacity, and all the clients being here. And then I have the problem we just saw right before. So it's a special case of this one. So now what is this matrix secretary problem? And I know some people get scared when they hear about matrix. So let me try to lower that shock a little bit. I'll actually mostly talk about one example of matrix and explain everything using that example. But whatever I do will work for any Matroid. So let's still just try to understand what is a Matroid. Or maybe first try to maybe explain what is the matrix secretary problem, and then I explain to you what a Matroid is. So here we can select, again a secretary problem, we have a ground set M. We want to select a subset thereof, so number of secretaries of that ground set. Before this used to be the green little dudes I had everywhere, right? And of total weight as high as possible. They reveal weights over time as before. However, the set I'm selecting has to be an independent set in a matrix. So the matrix is just a constraint. Before it was, clients I can actually connect from the server with unit path without exceeding the capacities. Right? This was the constraint. Here it's a matrix. Now back to what is a matrix? A matrix, now, depending where you talk to people in math or computer science, they may first say a matrix is a generalization of linear independence, or they may say a matrix is a generalization of forests. But let me just explain first the rules. So you have a finite ground set, and you have a subset there, a family of subsets thereof. Think of those as the feasible sets, the ones you can pick, right? So this family needs to fulfill 2 properties to be a matrix. I mean, strictly speaking, actually 3. It has to be non-empty, and it's to fulfill 2 more properties. One is that if something is feasible, or people in the matrix slang like to call those sets independent. So if something is independent, any subset thereof is independent or feasible as well. Makes sense beforehand, right? If I can serve a certain number of clients, I can also serve any subset thereof. That's good. If I have 2 sets that are feasible, and one is strictly bigger than the other one, then I can find an element in the bigger one that I can add to the smaller one and still have a bigger feasible set. So let me just do the two links from before, and that I mentioned before, the math and computer science kind of link. One is, imagine that, maybe I can just write this on the slide, that's probably more helpful. Imagine that your set n is a set of vectors, let's say v1, v2, and so on, finite set of vectors, the subset in R, say to the n. And think of I as being all the subsets thereof of linearly independent vectors. Okay. So let's just check. They fulfill these properties here. They form a matrix because it's a non-empty family. It's always non-empty because it contains the empty set, by the way. That's also a candidate, right? Indeed, if you have a set of vectors that are linearly independent, you take a subset thereof, they're also linearly independent. And you have the so-called augmentation property in linear algebra, where if you have two subsets of vectors that are linearly independent, and one has more vectors in there than the other one, so it spans a larger space, right? So you can find a vector from the larger space you can add to the smaller set of vectors and still get linearly independent vectors. That's one example. And the other one is that I would like to highlight, and I want to fix the other one in what follows, because we're here in computer science. So it's forests. Pick any graph and declare n to be the edges of your graph, and I to be all the forests of your graph. Indeed, any subset of a forest is a forest. And also, if I give you two forests, one with more edges than the other one, then you can always find an edge of the bigger one you can add to the smaller one and still get a bigger forest. One way to see this is if you have more edges here in your forest, you have fewer connected components than you have in this forest. This means at least one of the edges over here will connect to different connected components over here. Just add that one, and you have a bigger forest. And that's the only slide where I taught you a little bit of matrix slang, and I hope we can then, I'm happy to repeat things if anything is unclear later on. So again, it's the example of graphic matrix. Here's a graph, and as I said, ground set are the edges, independent sets are forests. And now I would like to introduce what's the rank of a set. Let's pick any subset of the edges S, the right ones here, just an arbitrary subset. It's not a forest, it's not even connected also, so it's a general subset. Then the rank of S is the largest forest you can find within. That's the size of the largest forest you can find within red. So from here I can find a forest. The largest one is, let me pick one largest one, there's many. That's the largest forest I can find within the red edges. It has, let's try to count that. It has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 edges. So the rank of the red set, rank of S is 10. What's the span? The span of that red set are all the edges that have both endpoints in the same connected component. What it means is if you add those, the rank is not going to change, right? That's the way it's defined for a general matrix. The span is all the edges. If you add them, the rank is not going to change. Okay? But to think of in a graphic matrix, both endpoints in the same connected component. And what's the basis? A basis of your matrix is a largest set that's independent. In connected graphs, those will be spanning trees. Okay. So what is now let's just look at an example of the matrix secretary problem for the graphic matrix. So you will just see edges popping up. Maybe this one has weight 9, you have to decide, do I pick it, yes or no, and you have to pick a forest. Let's pick it. Say red means I pick it. 3, let's not pick that one. Let's pick 7. Let's keep going. This one I cannot pick anymore. It will create a cycle, right? I have to pick a forest. And that's it. Right? Let's say it's the end of the procedure. And of course, what I want to do is I would like to find and have an algorithm that returns an expected weight as large as possible, and we will measure the quality of the algorithm in terms of its competitive ratio, meaning the expected weight of the algorithm we use divided by the max weight independent set here, the max weight spanning tree in that graph. So let me give you a procedure. It's a procedure by Carul and Paul for getting a constant competitive. It's a constant competitive procedure for the matrix secretary problem on graphic matrix. And I think it's a beautiful procedure. It's a very elegant procedure. That's why it's nice to get to warm up. It's a good one to look at the beginning. Let's say this is your graph, and you know the edges of that graph get revealed. You have no idea what the weights are. What you can do is just choose an arbitrary numbering of the vertices. Let's pick that one. Now look at two different orientations of the graph. In one of them, I directed all the edges from higher to lower labels, and in the other one, the other way around. So those graphs will naturally be acyclic. Makes sense. And what you see here in this red arcs I show here, those are just all the arcs that are entering a certain vertex. Let's do a quick observation. What I could do is I could say, let's just focus on this left-hand side graph for the time being, on this orientation. I could say, let's just pick for each vertex at the most one of the incoming arcs. It's not the problem I have to solve. I have to find a forest, I have to pick a forest, right? But if I do so, that's just two observations I want to make about that. One is if you have one incoming arc per vertex here, then that's definitely a forest. Okay. So I'm restricting myself. But any output I give here will actually be a solution to the original problem. But now, what can I do if I say, I mean, what is a natural strategy if I say, oh, I pick at most one of each of the red arcs here? I just run the classical Dinkin secretary algorithm on each of those bundles. Right? So just run it in parallel. For each vertex, you have one algorithm running. Whenever an edge appears, or now it would be an arc, it's a directed edge, I just look, oh, where is it incoming? Here it's vertex 5. Then I feed this into Dinkin for vertex 5. Right? So Dinkin will guarantee I will actually get among those arcs the highest weight one with constant probability. Remember, 1/e is the probability, but it doesn't really matter. The constants don't matter that much. I just care about getting a constant for time being. So that sounds good. Now the question is this a good procedure, of course, right? So far it's good. It's a procedure that will return a forest and to certain guarantees, but we don't know yet, but it's a good procedure. So it turns out this is not going to work out easily that way, but what we're going to do is we will actually, for probability 50%, run the algorithm on this graph, and with probability 50% run it on that graph. And the idea is that, I think I have a line about that. The idea is that no matter, think about any spanning tree, about the optimal spanning tree in the graph that you want to, say it's the max weight spanning tree that I'm drawing here. Let me, so you don't see the weights. I didn't add weights here. I just want to make sure, I don't want to overload the picture. And let's make sure I do something somewhat interesting. Let's say this is a max weight spanning tree. So I have to compare against that spanning tree, my solution. What I can do is just for analysis purposes, I can root it anywhere. Let's root it here at vertex number 1, but it doesn't matter where you root it. And just direct everything away from the root. So that's the way it will look like. Now, each of those arcs will be either here or there in one of the two graphs, right? Because every arc is directed both ways. Once it's directed one way here, and then the other way over here. Let's just look where they are in those graphs. So the one from 1 to 4 is in this graph. Then we have 4 to 5. I hope it took something that, I have a little mix of things. 7 to 8 is here. And then 5 to 3 is over here. 5 to 2 is here. And we have, 8 to 6. I guess I forgot that one. Let's see, 1, 2, 3, 4, 5, 6, 7. That looks good. But now remember, if I run my procedure here, I will get the heaviest arc among the incoming ones with constant probability for each of those vertices, even for the other ones, but for each of those. So what I get here will compare against the weight of the green edges. The same over there, because if I mix 50-50%, I'll actually get a constant factor. I lose a factor of 2 because I have to pick one of the two, and then I lose the Dinkin factor, so this is a 1/2e competitive procedure. I think it's beautiful. Oh, please, yes.
Just focus on this one.
Yeah.
For example, this edge is also constant, or maybe like 4 to 1.
4 to 1, exactly. It's a good point. So here, exactly, one could improve the analysis here, right? And say, well, actually, also for that edge, the 1/4 edge over there, I also would get it here with constant probability.
My question is, why do you need to consider both graphs?
Yes, what could happen is that maybe here it works nicely, but there could be another green edge that also links to 1, and I have to make sure that you're not only allowed to pick one of them, and if you have more incoming here, then you may lose. It could be even potentially even a super constant number of edges that are green, and the incident one. I have this with, yeah, maybe with 5, right? And here could not say that you can, yeah, you would have an issue if you don't do the analysis the way I did it. Yeah, that's the reason. It's a very good question. Thanks a lot for the question. Yeah. Oh yes, Alex, please.
Is it not the case that every vertex has a constant probability of getting its largest weight edge, in which case you're actually competitive up to constants with just like the largest edge for every vertex?
That's true.
As good as the...
Excellent. Yeah, exactly. One can think of it that way. So essentially, we're constant competitive against the harder objective, and the one where every vertex gets the largest weight edge. Yeah, that's true. Yeah, good point. Very good point. Yeah, sure. Yeah.
So in the original problem, it's not really a weight. I guess you define a weight. I don't know if 1/e is tight for the weighted version.
It's also tight for the weighted one. It's a good question. So in the original problem, I just said, oh, what's the probability to pick the highest weight one? I didn't really care about, maybe I should have emphasized this better. I didn't really care about what the actual weight is. I just want to get the highest weight one. But it turns out it's also, here you want to maximize the weight, exactly. And it turns out also for the single secretary problem, 1/e is optimal even for maximizing the weight. Yeah.
And I assume eventually, are we getting to the, because you gave a great example of serving users, and
yeah.
You did one of the 2 Matroid conditions for that. Is that a Matroid, or?
Oh, sorry, the one, oh, I should have, oh, thanks so much for the question. So it turns out the server example I gave you, that's also Matroid. So the subsets of green clients you can pick that you can simultaneously serve, that's the family of independent sets of a Matroid. Yeah. That's called a. That's called a gamma. Yeah, it's not easy. No, I mean easy. I'm not sure it's easy, but it's imagine. Let's check. So there's like, so as I said, one property is easy, right? The one I only verified just one. I think of the easier one. I kind of stuck the other one under the rock. Exactly. Exactly. The other one is what I have to show is if you have 2 sets of clients you can simultaneously serve. One is bigger one. Say 3 up here, only 2 here. Then what you can do is, so you can think of having a current flow that will actually serve these 2 clients. And now apply the max flow algorithm. It will find an augmenting path. It has to be able to find one because there's an option to get 3 clients, right? And max flow algorithm will always augment if it can. But what is another property of max flow is that it will actually not, anyone you serve now, you will still serve later after you augment along an augmenting path. And this shows the augmentation property. Yeah, you need to know that property of the augmentation algorithm. So thanks a lot for the question. But it's just a gap in what I said before. Perfect. So far, so good. So what's the big conjecture? What people would like to prove is people want to show that there's a constant competitive procedure for any matrix, for the matrix secretary problem. And this is wide open. And most experts believe it's true. The best it's known is a log-log rank procedure, log-log rank of the matrix. So what else has been found? There's been quite some, massive progress even on restricted graph classes. I showed you the graphic matrix. There's many more where people know how to get constant competitive procedures. This includes like so-called laminar, transversal, regular matrix, max flow, min-cut matrix, and so on. We don't need to go into those details. There's one more thing. There's certain different models where actually constant competitive procedures have been found, namely for the free order model and the so-called random assignment model. The free order model means that you can choose which one is the next secretary that gets revealed, not knowing its weight, of course. And I will talk about random assignment in a moment, so let me skip that for a time being.
So what I would, having made the transition at some point from approximation algorithms to approximation schemes, what I would say is under what restricted classes can yield a better than order 1, maybe a 1 plus epsilon.
Yeah. Very good point.
You'll address that later.
Yeah. So there's this has been studied for picking k secretaries out of n. So so it's kind of the easiest constraint for picking more than one secretary, and there you can get that. You can get factors that improve it with increasing k. It's not too hard to see. The question is, what is the best dependence on k you can get? Yeah. For other ones, it's for most of them include the single secretary problem as a special case, or many of them include that.
I guess there's a one over e lower band.
Yes,
presumably.
yes, that's true.
And it's probably for a very restricted class of matroids.
It's already for the exactly. It's already for choosing a single secretary.
Yeah.
So every matrix that generalizes that inherits that hardness. Yeah.
Okay.
Yeah. It's kind of annoying. Yeah. Mhm.
Mhm.
Kind of. Yeah.
So reality.
Yeah. It's reality. We have to live with the reality, I guess. Yeah. So but what's interesting, this is the aspect I want to highlight in also in this talk is all of these results. They heavily rely on this on the following fact that you know the full matrix up front. Meaning I give you the ground set, I tell you what are the independent sets thereof. Mhm. Remember the algorithm of Pal and Kurula I showed to you? This is an extremely nice procedure. I mean, I just said, oh, let's pick an arbitrary labeling of the vertices and then start orienting one or the other way. But I mean, you can only do that if you actually know the graph, right? And that's a bit of a strange feature because I mean, this algorithm here, for example, the algorithms over here, they don't need that. And now you may wonder, so why is that the case? The thing is that there's a general belief, maybe I should call it a belief, or just it feels weird that knowing the matrix would help you for the general matrix secretary problem. Why is it weird? Because let's assume I give you, so assume you know the matrix for the general matrix secretary problem. Then what I could do is, I could have my own matrix that I think is hard, I want to feed to your algorithm, but then I embed it in a much bigger matrix with a lot of elements that, for example, have zero weight, so have no impact. And you will learn little about, knowing the matrix will probably give you little information about the matrix I was hiding. That's not a really formal argument because you can observe 50%, try to learn where that hides. But somehow in a general, what I want to say is in a general matrix, it's much easier to hide stuff than in a specific matrix. In a graphic matrix, you can also say, or can also hide a graph. I just always give it a complete graph, right? And hide things. But there's not that much you can hide. For example, the Kurula-Pal procedure from before still works, no matter what you hide in there. It doesn't care whether you hide something bigger in a complete, smaller in a complete graph.
So I think I missed something.
Yeah.
You're thinking of an oracle model of access to the matrix?
Yeah, yes, exactly. What would be the model? Yeah, what would be the model if you don't know
there
it?
should
Yeah.
be I mean, so it's possible to prove potentially there's a lower bound, right?
Yeah.
Is there a lower bound
The-
on queries?
I see the number of. I mean, there's a lower bound on the competitive ratio. The best lower bound we know is still 1/e, even for a single secretary problem. So it's the same
no,
bound.
I meant, okay. I guess there would be the question would be a lower bound on the number of queries to achieve a given.
Oh, I see. I don't know of any such lower bound. That's a good question. Yeah, not sure about that. Yeah.
I mean,
There must be there must be a trade-off, right? The question is, where does it lie? Yeah, I don't know where it lies. Yeah. And so far, all those procedures that can be made in polynomial time. So I mean, of course, there's also two questions, right? You can say, I mean, to some extent, it's a stopping time problem. It's a purely information theoretic question to some extent, right? How much can you get out of the information you gather? You could ask a question that way, not even think about how many queries you make or how much computational power you need, right? And then you can, of course, also restrict the model and say, oh, actually, I want to be polynomial time. And then you can restrict it even more and try to understand the trade-off between how many queries I need to get something. So far, I mean, all of that is open. There's a general belief that probably you can do it at least polynomial time if you can do it, if you can get a one, but yeah.
So I don't know if you want to say anything about this. I mean, I feel like I've been given permission to ask this question by Elsa's introduction. But from a
Okay.
practical point of view, I mean, other than this is maybe a beautiful conjecture, can you say anything about why we would care about such an abstract problem as all matroids?
Yeah, it's a good question. Indeed. I think it's a nice abstraction that captures a lot of natural settings, but it's not, I mean, it's matrix is typically that you want to get a result from matrix and then you want to apply it for special cases. That's normally the way it goes.
Right,
It's not that,
right.
that you don't see a real life general matrix that seems a
You're
bit.
in a math department,
Yeah.
so it's okay, but.
Yeah, we see that in real life in a math
But I
department.
meant,
Yeah.
but I meant, do we think there'll be nice things that we'll learn from understanding this? Maybe we'll understand.
Yeah,
something.
it's a very good question. I think exactly. I think what you can try to learn. I think that's a key question. Also, we need to think about that question, right? I think one of the main things you can learn is that most procedures work still like Dinkin's procedure. They observe a constant fraction and then they take action. So I think the question is, what can you learn? What can you learn from such a distribution? I mean, from seeing a random constant fraction of the elements. What kind of statistics can you make that will help you to then make decisions based on those? And there's certain aspects you can learn also from a matrix. I will talk about that also here. It's about one thing you can learn. And I think the more we understand what we can learn, the more we can use that to maybe also in other settings to, I mean, not sure whether it's really in practice, but at least in other settings to apply that. Alice, please.
Oh, I guess I have a question about Bill's question, which is as far as number of like, I mean, I guess maybe you could have a rank or an independence oracle model of your Matroid, but it seems to me like you need kind of trivially at least linearly many, at least independence queries, just because if I do like a partition Matroid and like half of my elements are like say it's like a two-part partition Matroid, half of my elements can go into the one, half of my elements go into the other, except the other allows 0 elements or something like that. Then anytime I see an element, they need to decide whether or not I can actually like add it.
Yes.
And I need to decide which of the three things it goes into.
Fully agree. I think that linear is a trivial lower bound for getting any constant, right? Because because you need at least before you pick an element, you must check whether you preserve independence or you violate the yeah. But it's a very but I fully agree with you, Alice. It's a good point. Yeah. So even just to be able to pick a linear number of elements, you need to do linearly many queries.
Super linear lower bound though for queries?
I don't think so.
No.
Yeah. Yeah, I don't think
Seems
so.
like that.
Yeah.
I think that there would be.
I never really thought about it, so maybe, but
Okay.
it's yeah, interesting. So let's talk a bit about. So let me try to go to one special model that already was mentioned at the very beginning of when people introduced the matrix secretary problem, namely this random assignment model that I also mentioned in the last slide and said, oh, I will get back to it. So this moment is now. So how does that work? And so the adversary can still fix weights, but then the weights get assigned randomly to the elements. So let me give you an example. Let's look at our, and I said I will try to stick to graphic matrix. So here's our graph from before. So adversary can fix an arbitrary graph. Let's say if it's a graphic matrix example, let's say that one. And now here we have 8 edges. So the adversary will define 8 edge weights. I normally choose them distinct, but doesn't really make a big difference. How many do I have now? I'm an 8 now, good. And then what happens is those get assigned to the edges, but this process here, this is random, uniformly random. Okay, so the adversary is weaker, right? Before you could choose weights, graph, and the assignment. That's a random assignment model. And what's interesting here is also in that model, there people knew how to get this constant competitive procedure, but again, they needed to know the matrix. And I will show you how here you don't need to know the matrix. But I think again, the main message I want to convey, or the main interesting part, is not just this model and the result, but there's a certain aspect we can learn. Going back essentially to Phil's question, right? So I want to show you, without knowing the matrix, how you can get constant competitive in that setting. Yes, please. Yes. Oh, very good point. So if you have if you pick a single secretary out of n secretaries, then there's no difference. I mean, if you have randomness in one of them, you just see randomly the weights. But if you have another matrix like a graph, you have to pick a forest, then there's a big difference, because you cannot say, I mean, you cannot decide on which edge. I mean, you cannot assign a certain weight to a particular edge, but it'll be randomly mixed. Yeah, that's a good point. Yeah. Because there's a structural difference. The problem is in the single secretary problem, all the elements are equivalent, right, in terms of what is feasible and what's not feasible. But that's not true for the other models. So that makes a difference. Yeah. Thanks for the question. Yeah. Okay, let me recap Soda's procedure. Soda is the one who gave the first constant competitive procedure for that setting, but he had to know the matrix. Let's see what he did, and let's just look at that example. Okay, let's assume I give you that graph, and I tell you we're on random assignment. What would you do? Where do you expect to find heavy edges?
That's in a complete graph.
Exactly, in a complete graph, right? I mean, things get assigned randomly, uniformly at random, because there are way more edges in here. This is way more important that you're careful in that set here than outside, right? So you kind of want to protect the dense area from the sparse area, right? You don't want, but what I mean with protect, I mean that what you don't want to do is, you don't want to start picking edges outside here, like this. If I pick these 5 edges, right, then actually these 3 vertices are already in the same connected components. Yeah. So it can pick 2 edges less from the clique here. That's no good, because the clique has so many edges, it's likely to have many of the heavy ones as well. So we don't want this to happen, right? And that's what Soda observed. He realized, okay, I have to somehow shield the dense parts from the sparser parts. We want to protect denser parts. That's the message. How can we do that? And here he relied on decomposition known in matrix theory, but it's not that complicated. It's just it's called the principal decomposition. And for this, let's just agree on what is density, right? Just to make sure we talk about the same thing when I say density. A density of a set, which is a subset of the edges, is simply number of edges divided by the cardinality of the largest forest you can find in there. So if I pick a clique there, it's the density of that clique is number of edges. So let me try to do this live. Hope I'm not embarrassing myself. With 8 vertices, so 8 times 7 divided by 2 is like 28 edges, right? And what is the largest forest I can find in there? It has 7 edges, so it has density 4. That clique has density 4. But you can define it. You see that again, the definition is for general matrix. It doesn't use anything about graphs, but you can just think of it that way. Okay, so what's the decomposition? It does something very simple. It finds the densest subgraph first, then contracts it, finds again the densest subgraph, and keeps going. Quick reminder, you can find densest subgraphs in polynomial time. K-densest subgraph is hard. If I tell you your densest subgraph needs to have K vertices, that's a very hard problem. But if I just want to find the densest subgraph, this can be done efficiently, finding the densest subgraph.
In a graph.
In a graph.
But,
also in a matrix, by the way.
okay.
That's very good. In a graph, you can do this with flow computations.
Yeah.
In a matrix, you can do it with submodular minimization.
Okay.
It's one of those classic combinatorial optimization problems that can be solved in polynomial time, but it's
So
non-trivial.
you need to use separation oracle and ellipsoid type.
There are other procedures now to minimize submodular functions. The first ones used ellipsoid, and there's alternatives for that. Yeah, but it's again one of those. Maybe this links a bit to our discussion from before, Phil. So the thing is that if I look at a general matrix, then you would need one of those heavy hammer things to do it. But for almost any special case, there's much faster stuff you can do to actually get the
But
dense.
you're saying even for general matroids, there's a combinatorial algorithm.
Yes.
For that.
Yes, you can use a combinatorial submodular function minimization procedure to find the densest set. Yeah, exactly. So let's do it for this graph. So here I did it for you. So R1 is the densest set, then R2 and so forth. Let's just again think about that. So I said I will first find the densest one, I will contract it, and then the next densest one will be in the contracted graph, the light blue one. So and I like to think of it as follows. So it consists of that graph then, because I contracted purple, I guess, or violet. Yep. So I get that graph here. Then I contract this, and next densest one is green, and so on and so forth. So what we're gonna do is, what Soto then figured out is let's do the following. And now I will try to find a max weight forest in here, one in here, one in here, independently for each graph. And actually, if your first observation, and then return that. That's what I wanted to do. Yeah. First observation is if I pick a forest in each one of them, just look at the edges up there. That will be a forest up there. So that's good. Again, we're restricting ourselves to actually, one could think of it, we're restricting our problem to a more restricted matrix. So the feasible sets are a subset of the ones we had before. But that's okay. Right? That's one thing. Of course, the question is, I mean, first, how do you solve those problems here? What did you win by actually going to those graphs? And even if you can solve them reasonably well, why is that good? Right? Those are the two questions that remain. And there we need one main property, namely, it turns out each of those graphs has a special property. And this is called being uniformly dense. And it's easy to state. It just means a graph is uniformly dense. Let's look at this one here. If the densest subgraph therein is the full graph itself. And it's not hard to prove. If there were an even denser subgraph in here, you should have split that off first and then go to that one here. That's essentially the intuition behind it. This intuition really can be made formal quite quickly. But let me just leave it at the intuitive point here. So, and what's nice about uniformly dense graphs is here all the elements are kind of equally important. So it's relatively easy to get a good matrix secretary procedure for such a graph. It behaves similar to just having to pick k elements out of n. I mean, one has to think a bit more about it to be precise, but let's see. Okay, so formally, the key insights were, so we talked about that already. So it turns out for uniformly dense matrix, or here graphs, it's not so hard to get a constant competitive procedure. We still have to see whether that compares, whether what you get compares against the max weight spanning tree up here, or max weight forest up here. And that's the first statement. One can also show that it turns out if you look at the expected optimum weight, I mean, the sum of the expected of the max weight forest here plus here plus here, then that will be that is the same as the expected weight up here. So why do we have an expectation? We have an expectation because the weights get assigned randomly to the edges. That's what we take the expectation over. Okay. So this just means, okay, it's good, right? If you get constant competitive for each one of those, because I return the union of them, so I get the sum of their profits, I will be constant competitive for the original problem. How am I doing with time? We'll skip some stuff, but that's okay. So here I have a slide explaining why you can how it can be constant competitive on a uniformly dense matrix. Let me just give you one quick. It's slightly different to what Soda did, but it doesn't really matter. It's just a slide. It's a variation, one could say. Essentially, what you can do is you could just say if you have a clique, for example, you just look. What did we say? 28 edges, right? And I can pick 7 of them. Essentially, what you can do is you can batch the edges. So I will look at the first constantly many and try to pick the best one of those, and then again and again and again. And of course, I can only pick an edge if it doesn't create a cycle that I picked so far. And it turns out that is good enough. They will already give you a constant comparative procedure. Because things are assigned randomly, it's very unlikely that in the event that when first the heavy edges will be spread among the buckets you make. So it's unlikely they're all in the same bucket, right? And second, it's unlikely that what you picked beforehand in prior iterations will span precisely that heavy element that comes later. Essentially, those are the two reasonings one has to make here. But let me skip that slide. I mean, it's essentially a foolproof, or an almost foolproof here. I could go through, but let me skip that. It's not more than that. Yeah. So now let's go to trying not to use the Matroid. So it turns out that, of course, we cannot compute the principal decomposition. So this is this composition of densest set, next densest, right? We cannot do that without knowing the Matroid or graph up front. Mm-hmm. And it's actually hard. So what would be nice is, now we go back to the question, what can you learn, right? What would be nice is if I gave you an edge. If you could tell me, it's pretty likely that one will be in the orange, in the green set, for example, in the third heaviest one. But this seems very hard to learn. At least I don't know how you could learn this. I still would like to use the same approach we saw at the very beginning for Dinkin's procedure. So I want to observe a constant fraction. So say 50%. The constant I don't try to optimize constants here. And then try to see what I can learn and then see how we use that. Right? So what can we learn from a random 50% of the elements? And what I suggest here is, we suggest that you don't try to learn specific densities of where specific edges lie. Try to learn what we call the rank density curve. It is the following. Here's again the same graph from before. It's a graph that, so you look, it's a plot, rank against density, where you look at the highest density and then you just draw a horizontal line for the rank it has. So the rank of that was 7, right? You can pick 7 edges here. A forest of 7 edges exists in that clique. So it should be 7. And then take the next densest set. So R2, the density seems to be 2.5. I didn't check, but let's just hope that it is right. And then it's rank. So it's rank, again, the rank in the graph, and you contract the purple part. So they would have 1, 2, 3 vertices should have rank 2. So this is 2 units, and so on and so forth. I want to learn that. Just that curve. I don't want to learn specifics about which element lies in which part. I just want to learn the curve first. And so the way it's going to go is, we showed 2 statements. First, it turns out that with the that if you observe a random 50%, that's the set S right up there, a random 50% of the elements, and this is just the graph restricted to those edges. So the matrix restricted to it. So just look at the subgraph, right? And then what you can do is you can look at the rank density curve for that graph. Mm-hmm. Then it turns out that rank density curve is close to the one of the original graph. Let me be more precise what close means. Right? Of course, you have a subgraph, so the densities will be generally lower, right? So it's definitely not, you will not find denser sets than what you had originally in the graph. So it has to lie below the other rank, the true rank density curve. And that's the same holds, of course, for the complement, because that has the same distribution. I sampled 50%. So what I don't see, and it's important to make statements about both on one hand, because I mean, what happens is I will run my procedure on this and what's left, right? So I have to make sure I learn something from here that I can use on what I have not seen so far, right? That's important. So what we state here is that actually both of these rank density curves will be close to the original one. So they must be close to each other. So I can learn from here what I should do here. So now, what does close mean? What do I mean close? So now I like to plot those rank density curves in log scale, because everything, the errors we have are always constant factor errors. And then it's just like a constant distance in that graph, right? Makes just my life a bit easier. So it turns out that there's a good chance, good probability, constant probability here. The rank density curve of what you observed will be in like a tube that goes, a constant tube or a constant factor tube below the true rank density curve. So I may not be able to understand what this density is or what the highest density is, but I get one that is a constant factor lower than I will see. And I may not get the true rank, but I will get one that's at least a constant factor lower of the true rank. There may be more steps as well. It doesn't need to have the same number of steps, right? This red curve can have more steps potentially, but that's how it works. And then once we have that, we can, and then we learn that, so we also prove that, if we know actually a good approximation of a rank density curve, then we can get a constant comparative algorithm, and then you just have to combine. You first learn it, then you apply it on what you've not seen so far. About 10 more minutes, Alice, right? Good, perfect. And this will lead to the result. Let's start with an instructive toy case first. Let's assume that the true rank density curve is well separated, meaning that its steps are large. So there's always constant factors here and here. So they don't have many small steps. The way we will then reduce to that case later is we just simplify. If you have a rank density curve that has many steps, we will simplify to a coarser one. And let's assume for the time being that we know actually the rank density curve of the matrix. Let's just start with that problem. So we did the second part essentially. How do we get a good procedure if you know the rank density curve? And on top of that, I assume it is well structured. So I was take a bit more, it's a bit nicer assumption, but I actually have to show. So what we want to do is we want to learn a large fraction of each ring of this principal decomposition. Remember the different colors? And here we need the notion of the densest subset. Let me just do it on an example. You don't even need to read the whole part up there. Look at an instance of the graph here. For any subset of the edges, I will denote by DSH, let's say DS2, let's pick 2, for example, for H. That's the largest subgraph in black that contains 2 disjoint forests on the same vertex sets here. It's essentially the largest 2-dense subgraph you can find in there. Let me just show you one thing. So this red set, so there's like orange and brown are each is a largest forest in the red set I picked. So two disjoint of those, the disjoint largest forests. Right? Maybe even some extra edges the dashed ones. I don't care about them. Let me go back to the red set just to see it once more. So DS2 is the largest subset of edges you can find. So that you can in that subset of edges, we can talk about the largest forest. And there are 2 of them that are disjoint. Okay. And with this problem. And possibly some other things. Exactly. Yes. Exactly. Possibly some more things. Exactly. Good. So why is that useful? We show is that. So essentially, how should you think about that? Why do we talk about that even? So now there's a random notion coming suddenly on a random slide. So the reason is that, think of it as follows. With our the original matrix, I would like to learn, now, so I'll actually see only a 50% fraction of the original matrix first. Now, what I want to do is, having that 50% fraction, I want to look at densities of what I've observed so far of the sampling phase. And this will be such sets, essentially. I have a set S, and I look at what is the, for H equals 2, for example, what is the largest 2 dense set, largest 3 dense set, and so on and so forth. It's essentially the dense sets of what I observe. That's why I define it that way. I just want to give the main ideas of what one can show here. So what one can show is one of the technical results, and that underlies the whole procedure. One can show that if you have a matrix, let's go back to what we actually want to, what do we want to obtain? I want to be able to learn those steps, remember? So look at one step. Maybe it's a big clique. If I see a constant fraction of a clique, right? It's pretty, let's say 50%. It's likely that this is still a pretty dense set, right? The density should be in an expectation. It's precisely half the density, I mean, or roughly half, depending whether I create more connected components, right? But you would expect to see a density of about a half, right? So that sounds good. Now you could say, oh, that's great. So it's easy to learn densities, right? If there's a dense set, you observe half of it, it will essentially be half dense, right? And there's a danger with the reasoning. The danger is that, I mean, of course, you will not the full set will be half dense, only parts of it. There will be some less dense parts as well. And now what could happen, a correlation could happen. Namely, the areas where you observed more elements that then look dense to you are those where there are fewer elements left to draw later on from, right? Remember that later on I have to draw elements. I mean, I will see the remaining elements, and I want to pick the remaining ones. But the worst that can happen to me is I have or one of the bad things that can happen to me is I have, for example, the 8 clique of our example. In the sample, I see all of the 8 clique. Then I say, oh, let's protect all of it. That's great, because I found a dense set. But it helps nothing, because there's no edge left to pick from, right? So somehow we have to prove a statement that says, if you look at what you observe, and there's a dense set in there, that actually with high likelihood, there will be many elements that are spanned by that set. Therefore, if I protect the set, I will actually protect a lot of stuff I can pick from later on. That's what those statements say. It turns out that these sets DSH have that property. It turns out that what is spanned by such a set, if you not what you have seen, but among the remaining elements, I remove the sample set, is large, or it's unlikely to be small. Unlikely to be small. Right? That's what that statement says. That's good. So it means if you observe a dense set, it's likely there's a lot of stuff you can pick within the spanned by that dense set. The second statement says, oh, also that dense set is likely to be large or unlikely to be small. I have a proof for that. I will not go through that proof. But essentially in the toy case, this would mean if you look at, for example, let's look at some density. Let's say this density here. Then there's a set that has that rank actually of that density or higher, right? You have some part is higher, has in higher density, and then you have precisely that density here. So there's a set of that rank with that density. Now this statement says, oh yeah, you actually, if you now look at, think of this density, let's call this the density 3h. We use a factor of 3 here, 3h. If I look at a density that's factor of 3 lower, it's a log-log graph, so a factor of 3 lower means it's just a constant below, say factor 3, then actually you will see this set that is dense in the original matrix here will lead to a set that is dense for this density and still may not have that rank here, but has a rank that's close to it, maybe up to here. So you will see something that looks like that. Maybe it has some other steps up there, but essentially on that segment you should be above. That's what the statement says. You can apply this to each of those corners, and this will give you, and you have to make sure you can use a union bound, but this works out because this Chernoff bound is the Chernoff bound you see here is very sharp, and you can make sure you have concentration everywhere, and you will be close everywhere with a good probability. I'll keep it short. So let me skip the proof for that. I like the proof, but let's skip that. And then how do we go to general case? Just one quick slide, how this can be generalized. So let's try to put the pieces together. So the way things work is we first observe a random 50% of all the edges of our graph. Right? Now, quick reminder. The rank density curve, so rank RD, right, of what you observed and what you did not observe, again, they have the same distribution, what you observed, because I observed 50%. They are good approximations of the one of the original matrix. So they are close to each other as well. That's what I wrote here. The curve is the one that you observed is close to the one you did not, the one in which you work on later on. That's good. Then what we do is, so here we have now many steps. The reason from before, I kind of like that steps are far apart, that things don't start to overlap. And I know that I can apply, also get concentration by applying for only a few steps, this Chernoff type result. Right? The problem would be also to get concentration here if we apply it to every little kink here. Right? So what we then do is, we then simplify the curve. We don't look at the actual curve, but do as if the curve looks a bit different. This will lose a little factor, but it'll make it have the shape, essentially the shape we've seen before, the one with the big steps. And then we just run the algorithm for the toy example. the toy example algorithm, what it does is it just protects those. So it knows that if we have a density here, so it tries to protect the densities that we observe in the set S, essentially. One has to be a bit careful. I'm sweeping a few things under the rug, but essentially those are the ideas. Let me conclude. So I'm still, yes, it's time. So there is all this, a no non-competitive procedure for the random assignment model without knowing the matrix. I think, again, the model, I think, is a nice model. It has been, I mean, it has been asked at the beginning. There's been papers on it later on. So it's nice to solve. I mean, it was an open question. It was nice to solve that one. But I think what's probably more important is densities is something we can learn reasonably well. So hopefully one can use that also for the general conjecture. So up here, it's maybe from what I know, it's the first well-known matrix secretary problem variant for which we now have a no-one procedure without knowing the matrix. But of course, the big conjecture remains open. Now you may say, so how can we use those facts for the general matrix secretary problem? Because it's so different, right? Here used so heavily that weights get assigned randomly. Why should we even try to protect the dense area? It makes no sense because the adversary will choose the weights. There's no reason that the dense area is useful. Indeed, you should not apply it that way. But what one could, for example, do is, and also this has been done in other procedures, you could observe a certain constant fraction, say a third, for example. And then what you could do is you could say, now let's look at the max weight spanning tree of what you observed. And now let's observe another third. But when I observe an element, if it does not improve on that spanning tree, I just ignore the element, right? It anyway is not part of a max weight spanning tree. So people call the elements that do improve often improving elements. They could apply the result on just the improving elements, for example, right? So then I don't suffer that the adversary can, of course, completely fool me by just assigning the weights up front. But I'm not sure, I mean, it's not that easy to make it work. But just to give an idea of why I hope at least, hopefully someone will be smart enough to see how to use that in a way, as one of many tools probably to resolve that conjecture. Whether that will be the case, I can't tell, of course, but that's at least my hope. Yeah. Okay, thanks for your attention. Any questions? I'm happy. Yeah. Sure.
Section.
Yeah, there's also. It turns out we also have a paper on that one. So one can essentially for most matrices we can, for many, if you can solve them separately, we can also use soft intersection under some certain properties that have to be fulfilled. Yeah. But it's this certainly. I mean, but it's. Yeah, exactly. But there's still very little is. I mean, there's a lot to be explored there. This is maybe just the first step. Yeah. Thank you.